So either we need to subnetting when we assign some of the host bits to network, so we create more networks, or in supernetting we assign some of the host bits of the network bits to host, to make the network bigger and less blocks. Supernetting is almost eliminated by the using of classless addressing. So classless addressing will eliminate the need for supernetting almost. Now we'll talk about classless addresses. So in the previous scheme, in classful addressing, each address will belong to a specific class A, B, C, or D, or E. Classless addressing was designed to overcome the address depletion. As we said, many addresses in class A, class B almost were not used fully, because you see, as we said, so an organization maybe have a class A address which can assign more than 16 million host addresses, but they don't have this number of hosts. So most of the addresses will be wasted in this way. In classless addressing, there is no classes, but the addresses are still granted in blocks. So you still have blocks like in other classes, but here there's different way of assigning these blocks. When an organization, for example, small or large, needs to be connected to the internet, it is granted a block, a range of addresses. The size of the block, of course, varies based on the nature and size of the entity or organization or institution or whatever whoever is applying. So they may need a large number of large blocks or small blocks. They will be assigned. To simplify the handling of addresses in classless addressing, the Internet authorities impose 3 conditions on classless address blocks. So every time you or an entity is assigned a block, the block should satisfy these conditions. The first condition is addresses in a block must be contiguous. Contiguous means if this block is 16 addresses, so first one is 32, 33, 34, 30, until you go to 16, which is 47. So you cannot have, say, for example, 32 and then 36. They should be contiguous. The condition 2 is that the number of addresses in a block must be power of 2. So you either have 2 to power something, 2 to power 2, 3, 4, whatever. So in this case, for example, it's 2 to power 4. So the number of addresses in each block, the organization is granted a block. The number of addresses in the block should be power of 2. The first address must be, so the first address in this block, this one, must be evenly divisible by the number of addresses. The number of addresses is what? 16. So this one, of course, you convert it to decimal, or you do it by, so you divide this by this. There should be no remainder, yani evenly divisible, no remainder. Okay, so you can't divide, you should be able to divide the first address by the last address. We see some examples now. So let's see this example. We can see this example and see that the three conditions apply here. The IP addresses, the addresses are contiguous. We start 32 until 47. Or if you go in binary, there one follows the other one. So they are contiguous. The number of addresses is power of 2 because you have 16 addresses. 2 to 4 equals 16. So the condition 2 is true. Now let's see condition 3. The first address is divisible by 16. This address, when converted to decimal number, convert this binary to decimal is this one, then divided by 16, the result is this one. There is no point something. There shouldn't be any remainder. So it should be evenly divisible by 16. The first divided by 16 should be evenly divisible. Okay, so the three conditions that we said apply to this example. We'll use the slash notation in classless addresses. So there's a better way to define a block of addresses. You have to select any of the addresses. So this is the block. It contains 16 addresses. So you take any of these addresses, for example this one, and do the slash, then the block mask. So we'll use the slash notation. In IP version 4 addressing, a block of addresses can be defined as xyzt/n, in which xyzt defines one of addresses in the block. Okay, so xyzt can be any of these addresses, but normally we'll use the first address. And the /n defines the mask. So what's the mask? So the block is complete by giving one of addresses slash the mask. The address and the slash notation completely defines the whole block. The first address, the last address, and the number of addresses. So how you, if you have, for example, this block, what's the first address in the block? How you do the first address? You see here it says 28/28 means the prefix here is 28. Okay, so 28 bits are for network. So how many for host? 28 minus 32 minus 28. So 28 for network, and 32 minus 28 is for host. So to find the first address, you just you see 32 minus n, this part, rightmost bits, set them to 0. So in this case, for example, in this address, you see how many bits left? 4. 32 minus 28, 4. So you set the last 4 rightmost bits into zeros, and you'll get the first address. The last address, you set these 4 bits into ones. So you get the last address. A number of addresses in the block is the difference between the last and first, of course. In this case, it will be how many, of course, or you can easily calculate it as 2 to power 32 minus n. N in this case is, you see, is 28. Okay, so the first address in the block, you assign these bits to 0, and the last you assign the host bits to 1. So you'll get and the number of addresses, of course, is 2 to power 32, because the IP address is 32 bits. And now we have n, which is 28 in this case for network. So what is left for host is only 4 bits. So 2 to power 4, in this example, it's 16. So we have 16 hosts, or 16 addresses, number of addresses in this block. When an organization is given a block of addresses, the organization is free to allocate the addresses to the devices that need to be connected to the internet. So, for example, you've given this block of 16 addresses. You give these addresses to your devices, and the router also, the interface of the router will need an IP address of these IP addresses. The first address in the block is normally not assigned to any device of these devices. It is used as the network address that represents the organization to the rest of the world. So anyone outside of your network will see you as the first address in this block. Okay? The organization is connected to internet. Of course, you need a router. The router has 2 addresses. This is the internal, this is the external one, which connects to the internet. They should be on different networks. One belongs to the granted block. This is your block. Sorry, this is the block, your block. This is another address. The other belongs to the network that is at the other side of the router. This one. So they are different. Maybe the n is different than this 28. Okay. We'll study routing in more detail later. We have some hierarchy in IP addresses. You see, like telephone numbers, so you have area code, for example, and exchange offices, and then the subscribers. In phone, in IP addresses also, we have some hierarchy. We have net ID and host ID. So the network prefix is also some sort of hierarchy. So in class for addressing, we have only 2-level hierarchy if there is no subnetting. Okay, so without subnetting, you have 2-level hierarchy. You have the net ID and host ID. But with subnetting, you can have any number of hierarchy. You can have something like this. But without subnetting, you only have this hierarchy, 2-level. Level 1, level 2. Okay? You can achieve more levels of hierarchy using subnetting. An organization that is granted a large block of addresses may want to create clusters of networks or subnets. The rest of the world still sees the organization as one entity. All messages are sent to the router address that connects the organization to the rest of the internet. The router routes messages to the appropriate subnet. The organization, however, needs to create small subblocks of addresses, each assigned to a specific subnets. The organization has its own mask. Each subnet also have its own. So you'll have subnet mask, then the organization will have a mask, then you create subnets. We use some examples to explain these things. So assume the total number of addresses granted to an organization is n like 16 in this example that we've seen before. The prefix length slash is n. Okay. The assigned number of addresses in each subnet network, you make it n sub. So the original, for example, was 16. You want to make it, for example, n sub to 2 or 4 or whatever. This should be always smaller than this because you are subnetting. The prefix length of each subnet is n sub. Okay. So n sub will be different also from n because you are taking bits from the network ID and assign them to we are taking bits from the host ID and assign them to network so that the subnet will be different. The following steps need to be carefully. These are very important. You have to follow these steps when you do subnetting. Okay. Number of addresses of in each subnetwork should be power of 2. You cannot have, for example, 3 addresses in one subnet and 7 addresses in another subnet. We always need to have power of 2. So if you are asked to create a subnet of 3 addresses, 3 is not power of 2, so you'll choose this is important. You have to know how to design subnets. So to design subnets, we assume these things first. The number of addresses, original number before subnetting is n, and the subnet mask, prefix length is n. So this is the original without subnetting. Now, when you do subnetting, you'll have a different number of hosts in each subnet. So for n for subnet, and the prefix also will change to n sub. So to design the subnet, we have to follow these steps. We have to make the number of addresses in each subnet power of 2. So if you are asked to make a subnet of 5 hosts, you are not going to use 5. You're going to make it the bigger number than 5, that is closest to 5, of course, and power of 2. So power 2 to power 2 is not. So you have to go to power 3, which equals 8. So we'll use 8 addresses in first or in the block or subnet. Prefix length for each subnetwork can be found from, you see, So you assigned, you said I'll take 8, put 8 hosts in this subnet. So the prefix length is easy to find now. 32 minus log2 of n sub. So n sub in this case 8, log2 of this is 3. So it will be 32, for example, minus this one. We'll see the example in the coming slide. The starting address in each subnet should be divisible by the number of addresses in that subnetwork. Okay, the same condition as we said before. To achieve this is the important thing. Okay, so when you design to achieve this condition, you have to first assign addresses to the larger subnets. Don't start with the small or the medium. Start with the larger subnet, and this condition will automatically be achieved. Okay, so we have these 3 steps in designing subnets. Let's see an example, and everything will be clear. An organization is granted a block of addresses beginning with, so this is the block, okay? The block, this is the slash notation. This is a classless address, okay? So the organization needs 3 subblocks. So it's only 1 block here. We want to make it 3 subblocks. Each block one of them will have 10 hosts, 1 60 and 1 120. So we need to design the subnet. Okay, so firstly this is slash n. What's the n, capital N, the number of hosts, total number of hosts in the block? This is 24, and this is for network. So how many bits for host? 2 to power 32 minus 24. This is the total number of hosts, because we have how many? 8 bits for host. So it equals 256 addresses in the block. You see, 24 for network means how many left for host? 8 left for host. 2 to power 8 is 256 addresses in the block. The first address, it's given here, it's the granted. The first address, you need to make the, you see, the all host bits, 8 host bits, 0. So these are the host bits, 0, all 8 of them. So you'll get this IP. So this is the first address. The last address, you make all these host bits ones. So it will be 255. Okay, not 256, because 256 is the total number. You see, 0 to 255 is 256. So how you get the first address? You assign all zeros to the host address or host ID. On the last address, you assign host ID as all ones. So this one is this, and this one. Of course, the other part will be the same, because only this one is for host. The other one will be the same for the network. Okay. To satisfy the third requirement, as we said, the third requirement says the last address in the block, you see the requirement here, or the starting address in the subnet should be divisible by the number of addresses in the subnet, in that subnetwork. To achieve that, we need to do the first one, the biggest. So in this case, the biggest is 120. But 120 is not power of 2. So we go to the power of 2 close to this, which is 128. So what 2 to power what is 128? 2 to power what? 7. Okay. So in this case, you see, of course you can find it from here. 32 minus log 2 of which is, this is 7. So how many the n, the sub n sub will be what? You see, this is for host now. For network, how many left? 32 minus 7 is 25. So n sub is 25. Let's do it again. This 120 is not power of 2. So we go to the closest one. Of course, should be above, because you have 128. You cannot go to 64. You have to go to someone number bigger than that. So to 128 is the closest power of 2. Now, to find the number of bits for the network or the n sub, this is for host. So 2 to power 7 or 7 bits go to host. So how many left for the network? 32 minus 7, which is 25. Or you can do it this way. Total is 128. 32, because 32 total bits of IP version 4, minus log 2 of this one. Log 2 of this is 7. So it's same. Which one? You say here in what number to power 2 is 128 is 7. So you're doing the same thing here. So the first address in this block, we have 7 bits. You see, if we say X's, I need some space. So these 7 bits are for host. Now, to find the network address, the first address and last address in this subnet, you assign all the zeros to these bits. You get the first address, and all ones, you'll get the last address. So if you assign all zeros, you'll get this number, and if you assign all ones, you'll get 127, and the slash is always 25, because for this subnet. For the next subnet, you're not going to use this one. You go to the bigger, so biggest, bigger than the smallest. Now 60 is not also power of 2. So you go to 64, which is power of 2. Now, how many bits for host and how many bits for network? To find the subnet, you do the same. 32, because total number of bits per IP, minus log 264. Log 264 is what? What's this number? 32 minus what? Minus 6 is what? 26. So 2 to power 6 is what? 64. So this subnet can contain up to 64 hosts, and its mask is what? /626. You see here it was 25, 26. Here, how many bits for network? 25. Here, 26. So when the subnet is big, here you have less bits for network. Less bits for network. When they small, you have more bits for network, and so on. Because you see, you need more bits here for hosts because it's big. Here you need less bits because the subnet is smaller. So take bits from the network and assign them to host. So in this case there were 26 for network. In this case you assigned one more bit to network. So you have 26 for network, only 6 for host. In the last one you have 10. 10 is not power of 2. Again you go to closest power of 2, which is 16. Now how many bits for network? You say the subnet is now what? 32 minus log 2 of 16, which is 4. 32 minus 4 is 28. You see, now we have more bits for network and less bits, 4 bits for host, because we have less number of hosts in this subnet. So the first address, of course, you see, first here, last, when you all 7 bits assigned 1. In the next one, you start after this, so you start 128, and you can add, because it's 64, and you hear 63 to this number, you get 191. Now the last one will start at 192, and you add 16 minus 1, 15 to this, you'll get this number. You see, this is not the end of the block. So if you check the block and the other block and the other block, you have still unused addresses. You can assign 48 hosts with these unused addresses, because we just used 3 subnets, and these ones were left unused or wasted. Okay, I think we may need to do some more examples on subnetting. So we'll